Hi there and welcome to my YouTube video. Today I'm going to be giving a tutorial on how to delineate a watershed in R. If you're familiar with delineating watersheds, you've likely done this in a GIS program like ArcMap or QGIS, but it's actually really easy to do in R as well, using this package called whitebox, as well as elevatr, which lets you download elevation data or DEM files straight to R. This is kind of one of the more time-consuming or annoying things to do when you're delineating watersheds, and kind of ArcMap is going online and finding the right DEM file. So we actually can do this really easily using this elevatr package right here. But if you're not familiar with the workflow, generally what we're going to do is first determine our pour point, so the point that all the water is going to drain to. The second is going to be to fill in the gaps in our DEM. Oh, actually, we're missing something here. This should be download DEM file. So that'll be the second thing we do. And the third thing we do is fill in the gaps in this DEM file. And then using the whitebox package, determine the flow direction and the accumulation. And then extract the streams file from these. And then snap our pour point to the streams file. And use our snapped pour point and flow direction to delineate the watershed. So that's what we're going to want to do. But our first step, like I said, is determine our pour point. So this is going to be objective. This is kind of what you have to decide what you want to work with. But what I'm going to be working with is this this Ayers Brook in Vermont. The reason I'm choosing Vermont is because it's a place I'm familiar with, and I'm also going to want to use stream stats to kind of verify how effective this process was for me. So stream stats is a very easy to use USGS application that lets you delineate watersheds based on a pour point. It works very quickly. The state I live in, they don't have stream stats yet, so I'm going to use this point in Vermont so I can actually verify how effective this is. So my point is going to be in the Ayers Brook, which drains to the White River. This goes into the Connecticut River, and I'm going to pick right, just kind of like upstream of this confluence here with Adams Brook, so I can look at the Ayers Brook watershed. So I've extracted these coordinates into a CSV file, and now I'm going to want to read them into R. So I'll call this Ayers. I'm going to read CSV. Desktop YouTube. It's called Ayers Brook.csv. I can read that in. That's read in. And check it out. It's got our site and our Latin long. This might read in with other fields or some NAs, and you can just pipe in some things to just select these three fields and drop any NAs if that happens. The one thing about whitebox is you have to use absolute file paths. So what I'm going to do is just copy this, and then I'll have it on my clipboard when I need to use it later. So you can't actually use things in your global environment when you're working with whitebox. You have to use the file path. So it's a little bit it's more work, but you can just kind of copy most of your file path and just paste it in. Next, what I'm going to want to do is convert this table into a spatial feature using the SF package. So I'll do Ayers SF, and I'm going to do simple table as SF or spatial feature. I'm going to do that to the Ayers, and then this needs the coordinates. So the coords are going to be the long and the lat. You want to do long first. If you do lat first, it's not going to work. And then this actually has to be C. And it needs its projection, which is 4326. So I'll close that. I'm going to want to transform this actually to equal area. So 2163 is something. Why is this wrong? Nope, it's right. Let's see. Nope. No. Oh, did I load these in yet? Nope. Okay. Alright, that worked. Alright, like I said with the absolute file paths, we can't use this as our pour point. We have to write it to a shape file. So I'll do st write ayers sf. So I'll paste that in. Whoops. Paste this in. I'm going to call this ayers pour point.shape. It also needs a driver, and the driver is going to be a string that's called Esri shapefile. And then just to make sure I can use leaflet to check to see if my point is correct. And because it's a variable, I have to call it again. But yeah, so we're in Randolph, Vermont. This point looks very similar to the other one, just above Central Street. Yep, that's Central Street right there. Looks good. Alright. So let's go back up to our workflow. We've determined our pour point, we read that in. We need to download our DEM file with elevatr. Okay. So download DEM file and write raster. So what we want to do is call this ayers elevation. I'm going to use the tool get raster. I can use like an ROI here, like a region of interest of this spatial feature to kind of clip the raster in a way to what I want. So I'll call it ayers SF, and it needs a Z, this Z field, which is like the zoom. I've played around with this and it seems like 10 is the best for this process, but in general, if you have a higher zoom, then it's going to take longer to download, or a larger area, it's going to take longer to download. But this 10 was pretty good for deleting this watershed, so I'm going to use 10. Yeah, that took super quickly. It took like no time at all. Kind of mosaics things on its own, projects them on its own, downloads everything right here. So I can also plot this to check it out. That's our DEM file right there, and it was really simple to download straight into R, which is it's a really cool tool. So next, what we're gonna want to do is write this raster, because we need the file path. So write raster. We're gonna write ayers elevation, the file name. It needs the data format, and so the data format is going to be geotiff file. And that should be good. Take a second, but it's good. And yeah, so we have our DEM. We've turned our pour point. We've downloaded our DEM file, and now we need to fill in the gaps or the sinks in our DEM. That's the first step to deleting our watershed. And we're going to do this with the whitebox tools. So all the whitebox tools have this WBT prefix, so it's going to be fill depressions. You can see it takes a DEM file, it has an output, and then it's got these various other fields that have defaults. I'm not really going to play around with the other fields, but really it needs just two things, the input and the output. And most other things you can leave to their defaults. So the input is going to be our DEM file right here. Copy that. It's going to need an output, so I'll just copy most of the file path. And I'll call this ayers filled. And it's going to be .tiff. And then I think these are actually the defaults, but I'll just call them anyway. True, verbose, false. Let's see if this runs. Okay, that went pretty well. It only took tenth of a second. So let's name this fill depressions or sinks in DEM. So this is kind of like a chain we're going to use. So like we used our DEM to get the synced or the filled file, and now we're going to use this in the next step. And you're always going to be kind of using the output as the input for your next step. So we have filled in the gaps. We need to determine our flow direction and our flow accumulation. So determine flow direction. And so where it is, remember the WBT prefix. And for this, we're going to be using something called D8 pointer. So this is a flow direction right here. It's just got a different name. D8 pointer. And so, right, we're going to need our filled DEM, which is right here. Copy that over. And then we're going to need an output, so I'll just change the filled to floater. Floater. I don't really need to mess around with the output with other fields. Let's call that very quick. Flow accumulation is next. So this will be, what's this going to be? WBT flow accumulation. You can also, I think you can also do this D8 flow accumulation, which basically does the flow direction and the accumulation at once. But I did it in 2 steps, which is okay. Actually, I'm going to use D8 flow accumulation actually as well. I think there's a field in here that you can set as false or true, and that is basically like if you did this, if you already have a flow direction or you don't. So I'll walk you through that in a second. But we're going to take this flow direction file, copy it in, you get the gist of it now. We're going to want an output, so this is flow ACK, call it flow ACK. I'm going to need an out type, and those are going to be cells. And then basically there's some other fields in here that I'm going to do. Is flip false, glass false, PNTR. So the pointer, basically we have it, so I'm going to put true. I think that's going to work. And then Esri false. WG equal to null, and the rows null. I don't know how many of these fields I actually have to fill in. I think most of them are the defaults, but this one pointer I'm naming true because I actually have already done the flow direction here. Whoops. Something's not right. Let's see. Type cells clip. You can get a law. Let's see. Didn't work. Just check. So, interestingly, I do have the flow accumulation file in here. I don't know. So it worked. If I do alright, that worked. I don't know about that verbose mode field for some reason was acting up. The whitebox package in general is a little bit finicky, so things happen sometimes. But in general, that worked anyway, and I saw it come up in the file path. So I think we're good. So we have flow direction, we have flow accumulation, and we need to extract our stream files now. So extract stream files. So with this, we're going to be using the WBT extract streams. So the input is going to be our flow accumulation, which is right here. And then the output I'll call airs streams.tiff. And then with this, you're going to need a threshold value. And this kind of helps define actually what a stream is based on this threshold value. So I've played around with this, and I've looked at things online, and it seems like the best, or the value that worked best for me with this was 10,000. You might need to play around with this and see what works best based on these different thresholds, but for this I'm going to use 10,000. And this worked pretty quickly. So let's scroll back up. We extracted our streams file. We need to snap this point, our pour point, to that actual streams file. So I probably don't have to have chunks for all these things, but I'm just doing it this way, so I might as well keep doing it. And so to do this, we'll use the Jensen snap pour points. Jensen's just the name of the method, I think, that this one uses. So we need a pour point. The pour point is going to be whatever I named it. I don't know what I named it. This. Right, so this is our point that we made the shapefile. Point is that. What else does it need? The streams is going to be that streams file that we made. And then it needs an output as well. So output, I'll just put airs snapped .tiff. And then it needs a snap distance as well. So this is kind of the maximum distance that this will look for the stream file. So obviously our pour point isn't exactly on a stream, but we want it to be, and so this distance could be large or small. I'm going to have it as 10. I'm actually unsure what the metric is, what this number actually, what metric that is, but I found that the 10 actually works pretty well, but you might need to have a higher snap distance. So that's done. And now I'll just do this in here. Watershed delineation. So like I said earlier, for our watershed delineation, we need that snapped pour point and our flow direction raster. So with this, we'll do WBT watershed. We need our D8 pointer, which is the snapped pour point. Or no, the D8 pointer is going to be our flow direction, actually. So flow direction, right? D8 pointer. So I'll call that in. These are pour points, which is this snapped. Needs an output. The output call watershed. No, hold on. Ayers watershed. And then the last thing it needs, I'm going to call this going to be false. Oh, it didn't work out. Why is that? Huh? Okay, so this is actually a shape file. This snapped pour point. So we're going to call that. It might not. Okay, it worked. It. And let's see. All right. So we delineate our watershed. Our watershed is a TIFF file. We're going to want to convert that to a shape file so we can compare it with the stream stats delineation that I mentioned. So this is WBT raster to vector polygons, and I'll take our input. Output is going to be called Ayers watershed dot shape, and that should be good. All right, we're done. We've got our watershed. Let's see how it looks. I could plot it in R, but I think I'll just move to GIS for this part of this. But so YouTube vids, Ayers watershed shape. Let's see. That's that. We can come to stream stats, and I'll just look Randolph, Vermont. Where was our point? Right here. Right above Central Street, so we're in Vermont. We're going to delineate right here. If you've never used stream stats before, it's really easy to use. You can get different watershed characteristics such as percent forest or percent impervious cover, those type of things. But yeah, we'll just wait as this does its thing. That's our watershed. Looks a little oblong. I don't know, we'll see. We're gonna download our basin as a shape file. Layers. Cut. YouTube vids. Paste. Let's see. Refresh. And so you can see here, let me just make one of these hot, or I guess I should make one of these transparent. I'll make the Ayers watershed. Single. I actually haven't used GIS in a while, honestly. This is why I just rather do all this stuff in R, because I don't have to deal with this. Transparent, 50%. Does that work? No. I mean, I'm not going to play around with this anymore. I can't believe I forget how to make things transparent in GIS, but you can see they're basically on top of each other. They're basically the same. Yeah, so that's about it. I would expect like little differences given that our pour points are probably a little bit different. Also, our kind of the threshold for our streams might be different. Snap distance might be a little bit different. But in general, this is pretty spot on. So I think this is a really cool tool, a really cool kind of workflow that you can use to delineate watersheds in R. Obviously, you can make this like a lot more streamlined. You could make a function that did all this stuff. Maybe you could kind of batch process a lot of this stuff, but this is just kind of like a basic overview of this process of delineating watershed in R. But I think the whitebox kind of package has a lot of different hydrological applications that you can use in R, so it's worth checking out for sure. Alright, cool. Hopefully this video was useful for someone out there. You can leave a comment or like the video. Let me know if you have any ideas for any other tutorials I could do, but yeah, I hope this was useful.